Good afternoon, dear participants. My name is Konstantin Lukyanenko, and the topic of my presentation: investigation of the thermal aging effects on WWER 1000 materials for up to 60 years of operation. This work was carried out as part of the research project.
So the other side? Yes.
I'm representing PPT Center. We are a small engineering company and SME in EU classification. Our company mainly works for nuclear industry. My PhD works related to the investigation of the thermal aging effect. Here is the content of my presentation. Firstly, I will introduce you to the thermal aging effects and formulate the goal of our study.
Please speak up.
Then I will describe the experimental techniques used for artificial thermal aging and further investigate of its effect. After that, the result will be present mainly with the reflection of change in mechanical properties and the impact toughness caused by influence of thermal aging. And finally, the conclusion will be given. Sorry. In some materials, diffusion control precipitation mechanism is acting even at service temperatures. This process called thermal aging and leads to a loss of ductility, deformability, and toughness. The significant parameters responsible for this process are temperature, material state, and time. The two main phenomena causing thermal aging: the first is intergranular segregation of phosphorus in martensitic and granitic steel, and second, unmixing of chromium from solid solution in the ferrite of duplex austenitic ferritic stainless steel and in martensitic stainless steel. In Ukraine, operating 4 nuclear power plants. It's 15 power units, but one power plant is occupied. This table shows that most power unit service life have been extended. In Ukraine, the mechanical properties are controlled based on hardness result. However, this method has a large error during the measurement and recalculation. This slide shows the example of determining the mechanical properties using hardness value at different years of operation. As you can see, it is impossible to estimate the thermal aging effect. Regulatory documents state that thermal embrittlement is only taken into account for the LPV. According to this document, thermal aging does not affect on LTO, long-term operation. Also, thermal aging hasn't been determined yet. It could affect up to 60 years of operation. Therefore, the main task of the LTO project is to investigate thermal aging effect. To investigate these effects, 3 materials were selected for testing. The first is austenitic stainless steel cut from pressurizer surge line after 28 years of operation. The second is ferritic steel cut from reactor flash fastening parts after 30 years of operation. And third, it's ferritic steel cut from main silver piping in its initial states. And the normative mechanical properties shown in this slide. A laboratory oven was used for artificial thermal aging. This process was carried out at temperature 723 degrees Kelvin. The aging time varied from 252 to 39-44 hours, and calculate using this relationship, this equation. Sorry. Here T1 is the operating temperature, and T1 is the operating time of the operating temperature. To investigate thermal aging effects, 4 types of experiments were conducted. The first is potential test. For potential test, we designed and manufactured grips with adapters, which were mounted on our testing machine. This grip allowed to conduct experiments at high as well as at low temperature. At least 3 specimens were conducted for each temperature as well as at each types of materials. Impact toughness was determined using impact pendulum impact tester with a maximum impact energy of 300 joules. Given the small amount of materials, device was designed and manufactured for reconstruction. The Sharpie specimens using 1 broken half and 2 side inserts. The Sharpie specimens were reconstruction using laser welding. We used standard Sharpie specimens with a notch dimension 10 by 10 by 55. And similar to tensile test, grips with adapters were designed and manufactured for small punch test. The grip consists of upper and lower die, between which the specimens were placed the punch, as well as the grip bushing. Here also you can see one of the test graph and specimen before and after the experiments. To determine the hardness, we prepared the metal surface in advance. The test was carried out using Ultracon TM40 hardness tester. Using the equation which is shown in this table, we determined mechanical properties such as ultimate and yield strength, as well as relative elongation and reduction was determined. Oh, sorry. This slide shows the result of determining the mechanical properties of steel cut from pressurizer surge line. Also here you can see stress strain diagram before and after thermal aging. As you can see, it's quite similar diagram. And as you can see, thermal aging also almost have an effect on mechanical properties for austenitic stainless steel. This slide shows the result of determining the mechanical properties on steel cut from pressurizer surge line. As you can see, thermal aging leads to a decrease on mechanical properties. The same situation applies for main circular piping, also made of austenitic steel. We observe a decrease in mechanical properties. This slide shows the result of determining impact toughness. As you can see, the thermal aging leads to reduction of upper shelf energy and increasing of PBTT for ferritic steel, and slightly reduction of upper shelf energy for austenitic stainless steel. And conclusion. The main result that thermal aging leads first for ferritic steel to reduction of upper shelf energy and increasing the ductile to brittle transition temperature, and decrease on mechanical properties. And for austenitic stainless steel, it's slightly reduction of upper shelf energy and almost have an effect on mechanical properties.
Thank you so much.